as we move left to right across the periodic table. So as we go from K all the way to F, so as we move this way, from this side to this side, I use these as an example. You can look up any ones you want. It'll be the same trend. So as we move from here to this side, what happens to these numbers? They go up. So what happens to the attraction for electrons? They go up. All of the nonmetals on the right here want to gain. They want the basketball. All the metals over here, they don't want it. They're going to get rid of it. They're going to lose it. You need to know the definition and understand the trend. So what I want you to do, I don't know if you have room in your notes, I told you to leave 3-4 lines. I always put the marker somewhere and don't know where I put it. Really? Okay. I'm going to erase this. I want you to sketch a little graph somewhere near this if you can. This is bothering me. Thomas, do me a favor. Walk to the back door and take a left.
What's bothering you?
That light is off.
Oh.
Thanks. Come on back. Electronegativity on the Y and atomic number in periods on the X. Let's go get this down, Cody. So electronegativity, attraction for electrons, desire for electrons. I'll use that word sometimes. That's where I was going with she's in love with the ball here. She's attracted to the ball. Like a bug zapper. You ever see a bug zapper?
Yeah.
It's kind of disturbing, right? Poor bugs. You like pizza, Cody?
Yeah.
Like, love it?
No.
What's your favorite food?
I don't know. I'd say like red meat. Like
Red meat? So if I had a pile of red meat up here,
like
you would just dive right on top of it?
Oh, not so
Like a bug zapper? Imagine if red meat zapped us to death. That'd be cruel, right? Anyways, back to this. Electronegativity, atomic number in the periods. Raise your hand. What's the graph look like? As the atomic number in a period, so we always start on the left side here. Yep, we only do line graphs in chem. We never do anything else. What's this graph going to look like? There's really only 4 graphs you'll ever see in this class. That, or that.
It's going to be like that.
So it's one of those 4.
The first one.
And guess what? We really never use those either.
The first one.
Yes, what's that called? Direct relationship. So as we move left to right, the electronegativity goes up. Okay, that's a direct relationship. Now, there are some that might dip a little. It's not a perfect trend, but in general, as we move that way, this increases. I just spent a little bit of time on that, and that's fine, because this has the exact same trend if you can read. Not trying to be a jerk, but 400 is smaller than 590, which is smaller than 7. So as we move left to right, ionization does the same thing. So you could swap this out, or you could actually just go or ionization energy. So just add that to your graph. This is the exact same trend. The line would move because you'd have a different scale, right? So instead of 0 through 4 for electronegativity, we're going in the hundreds and thousands, but the trend is the same. The actual numbers don't concern me that much here. It's just the trend, right? So again, as we move left to right, nonmetals have high ionization. And that's because they have high electronegativity. One depends on the other. All right. What the heck is ionization energy? So I'm just going to erase so I have room here.
It's measured.
Okay. Dang it. Hold on. I got to write those again. What is it? K, Ca, Fe, P, O, F. 4 what? 19? 590, 762, 10, 12, 13, 14, 1681. Yeah? Yeah, okay. All right. Here we go. All right, I'm potassium. You want to help me out again?
Yep.
Okay.
I do not want to be in this camera.
Do you mind that you're on? Okay.
I like
All right.
waving.
So, only my 25 subscribers are gonna see you. So, all right. So ridiculous. Anyways, all right. So I am potassium. She is fluorine. All right. Again, jump ball situation. You know what that means?
Yeah.
Okay. So maybe the ball's on the ground and I grab it and you grab it at the same time. So both of us, we're fighting over it. Usually there's a lot of flopping around and stuff on the ground. We're not going to do that. All right, so I'm potassium, she's fluorine. All right? So when I say go, we're both going to yank on this as hard as we can.
It looks like she has a better grip.
I'm going to go 1, 2, 3, go. Don't pull too hard. 1, 2, 3, go. All right. Okay, there's a point to that. All right, so I'm potassium, she's fluorine.
What if she just like flew on
That's
the
why
ground?
I said don't go too hard because I was going to let go. All right, so obviously I for the sake of the demonstration, I let her have it. But in real life, those numbers, look at those numbers there. Okay, potassium would never win that. Fluorine would always rip it out of potassium. Okay, now I'm oxygen. She's fluorine. Let's do it again. Okay, so now I'm going to say 1, 2, 3, go. We're going to try and rip it out of each other's hands here. So I'm oxygen. Am I much closer to fluorine now?
Yeah.
Okay, ready? Go. Okay, did I put up more of a fight?
Yeah.
Why?
Because you're closer.
Because I'm closer to fluorine and my numbers are similar. Okay? Thank you. I'm good. What? Who said something about neon?
Amanda.
What is it? What's neon's value? What's neon? Go ahead, look it up. What? Ionization energy for neon. 2000. Is anybody? What about helium? Or is that no? You just looked up neon, right? What's helium?
2,300.
Anybody higher than helium?
No
Okay.
way.
All right. Why? Okay, yeah, that's actually a good point that you said brought that up. Why would noble gases have really high numbers?
Because they already have a balance.
So let's define
Or
this.
because they're over all the way to the right.
Yeah, it's full balance shell. You're right. All right. What is ionization energy? Gotta give me a definition. I tried to show you with the struggle. I'm gonna start you guys off. The energy. So ionization energy is the energy. This is the definition.
The energy used to.
The energy. I'm gonna say needed, but you could say used.
needed to get an electron.
Very good. The energy needed to remove an electron. So in our analogies there, our examples, Sylvia's fluorine. Did she lose the electron? No, she was taking mine. Okay, I was too weak to take it back. Nobody can take electrons away from fluorine. Okay, because fluorine is very strong. This number literally means it takes 1,681 kilojoules to remove one electron from fluorine. That's a big number. Okay, it's a big number. So there's 0.4 kilojoules in a banana. 0.4. That's 1,681. So think about how many bananas you would need to take an electron from fluorine. All right. So when you eat food, you get energy and you can do things. The energy chemicals get from certain areas, certain reactions, things, they can do something with that energy, like take electrons from something. So fluorine, it's going to take a lot of energy to take this from fluorine. Why does that make sense?
Because fluorine has a higher number.
Fluorine has how many valence electrons? Ronnie, you with me? Okay. Fluorine is 2-7. It has 7 valence electrons. It needs one more to be an octet, stable. So it doesn't want to lose anything it already has. Why is potassium's energy so low?
Because it has one.
Right, it has 1 valence, so it wants to lose it. So this is a very low number. When we were fighting over the electron and I was potassium, basically I just let it go because I don't want it. I don't want my electron. So this goes hand in hand with electronegativity, which explains the stable valence shell, which explains why they're in group 1, why they're in group 17. So these two terms explain a lot that we're going to use all year. This is why I teach it now, and then we're going to use this constantly. So it is important to remember the definitions, but also be able to explain it. So metals have low numbers because they don't want them. They want to get an octet by losing, whereas non-metals have higher numbers because they want to gain them, and then they're going to keep them. That's why these numbers are what they are, okay? So if you're still a little confused, that's okay. We're going to talk about this a lot. All right, so I got about 8 minutes left. I do want to show you the demo. But first, hold on, don't pack up yet. The demo only takes a couple minutes. First, I just want to at least title the next part of the notes here and explain where we're headed. So matter and energy. Matter and energy is the next unit. And let's define the word matter, and then we'll list some examples, and we'll maybe give some examples of energy, and then we'll go do the demo. Okay, so let's define matter. Matter is anything that has mass. Who said that? Good, Sydney. Has mass and no, just matter. Just defining what matter is. Anything that has. Oh, that's an and sign. I'll give you a hint. It's the definition of the word volume. It takes up space. Has mass and takes up space. And I'm going to give you like a flow chart next week. It helps you conceptualize better, but I'm just going to list it now. Atoms, molecules, compounds, mixtures. These are the terms that you need to kind of associate with matter. Atoms and molecules could be elements. Actually, a compound can be an element or a molecule as well. That's confusing, but that's okay. I'm just throwing all the terms out there. We'll talk about them next week. But yeah, everything. Right? I think I told you my joke. Maybe not. Why can't you trust atoms? Why can't you trust atoms? It's a really bad joke. Because they make everything up.
Yep.
Right. They make up everything, so you can't trust atoms. Atoms, molecules, compounds, mixtures, literally everything in the universe that's considered matter, almost everything, is one of those terms. Okay, an atom, a molecule, which are elements, compounds, mixtures. Okay. What about air? The air in this room, is it matter?
Yeah.
Does it matter?
Because it takes up space, possibly.
No.
Right?
Or my other favorite one is, what's the matter? The answer is yes. What? That doesn't make any sense. Air, does it matter?
Yes.
Prove it.
It's everywhere.
Prove it.
You're breathing.
Prove it. Prove you're breathing.
You're alive.
If you're alive. Prove it. Captain Jeffers thinks this is all a hologram.
Well,
And when you look into the sun, you'll see the true answer. That's what he told me yesterday. All right. Anyways, how do you prove air takes up space and has mass?
Where did that come from? I didn't know you were holding that.
It was in my armpit.
Yeah.
It was right up here, and I tucked it away. So, if you take a deep breath, take a deep breath. What do you feel?
Pressure.
Pressure. What's in there? Air. Now you can feel it taking up space, but I can prove it with a balloon. If we mass this balloon, and then mass this, would it have a slightly higher mass? Yes, because there's air in there that has mass. Is it taking up space? Yeah, you can prove it by letting it out. So air is a great example that some kids get confused about, okay?
Carbon dioxide.
Like carbon dioxide, right. All right, I'll pick up with that on Monday. Let's do the demo.